Hello, sir. I am Shashwata Mukherjee from Electrical Engineering Department, second year. Now, I am going to give a presentation on the topic number systems and logic families, that is, transistor logic and complementary metal oxide semiconductor, CMOS. So, first, we come to the basic introduction of the fundamentals of digital systems and logic families. Digital systems are the foundation of modern computing and electronics, and understanding their underlying principles essential for anyone working in these fields. We will explore the core concepts from number systems and Boolean algebra to the characteristics of different logic families. This presentation aims to provide a comprehensive overview suitable for both beginners and those looking to refresh their knowledge. We will delve into the practical aspects of digital design, including power dissipation and the latest trends shaping the future of digital systems. Next, we come to the basic number system representation. The first thing about this is that there are basically two types of numbers: signed numbers and unsigned numbers. Signed numbers representation is a way to represent the signed number, that is the integers, in binary using the most significant bit MSB to indicate the sign. If the MSB is the leftmost bit in a binary number, if the MSB is 0, the number is positive. If the MSB is 1, the number is negative. The remaining bits represent the magnitude of the number. Unsigned numbers are basically used for positive numbers, that is without sign. Unsigned numbers are represented using a sequence of zeros and ones. The value of an unsigned number is the sum of the values of its individual bits. The range of an unsigned binary numbers starts from 0 to 2n minus 1. Next, we come to the basic concept of signed number representation given by ones complement. Ones complement representation in a binary number: if each 1 is replaced by 0 and each 0 by 1, the resulting number is known as the ones complement of the first number. In fact, both the numbers are complement of each other. If one of these numbers is positive, then the other number will be negative with the same magnitude, and vice versa. The maximum positive number range in this ones complement representation is given by 2 to the power n minus 1 minus 1, and the negative maximum number range is given by minus 2 to the power n minus 1 minus 1. Next we come to the 2's complement representation. The 2's complement representation says that if 1 is added to 1's complement of a binary number, the resulting number is known as 2's complement of the binary number. That is, if we get a binary number, we need to find first its 1's complement and then add 1 to it in order to get 2's complement. Here also, the maximum significant bit if the maximum significant bit is 0, the number is positive, and if the maximum significant bit is 1, the number is negative. The maximum range at the positive number in this 2's complement representation is also the same. There is a 2 to the power n minus 1 minus 1, and maximum negative number is minus 2 to the power n minus 1. Next, we come to the Boolean algebra. Logic gates: AND, OR, NOT, XOR, NAND, and NOR. AND gate outputs true if only both the inputs are true, otherwise output is false, represented by symbol dot. OR gate outputs true if at least one input is true, the output is false if both the inputs are false, represented by symbol plus. NOT gate inverts the input: if the input is true, the output is false, and vice versa, represented by symbol inverted commas, also known as an inverter. XOR gate outputs true if inputs are different. If the inputs are same, output is false, represented by the symbol plus within a circle. Next, we come to the basic number system, that is the decimal, binary, octal, and hexadecimal number systems. Binary number system is a type of a number system with a base radix of 2. It is the foundational for digital logic due to its direct correlation with electronic on-off states, simple to implement in hardware. Next, we have the octal number system. The octal number system is a type of a number system with a base radix of 8, uses digits 0 to 7. It serves as a convenient shorthand for binary, where each octal digit represents 3 bits. Next, we come to the decimal number system with a base radix of 10, the standard number system for human use. Digital systems convert to decimal for user interface. Hexadecimal number system is a number system with a base radix of 6, 16s, uses 0 to 9 numbers and alphabets A to F. It's extremely useful in programming and digital design for representing larger binary values compactly. The table shows the representation of different types of numbers in binary, octal, decimal and hexadecimal, starting from 0 up to 1111 in binary, 0 to 17 octal, 0 to 15 in decimal and 0 to F in hexadecimal. Next we come to BCD, Gray code, XS3 code. BCD stands for binary coded decimal. Represents each decimal digit 0 to 9 with a 4-bit representation. Simplifies interfacing with decimal-based number systems like displays and keypads. For example, 8421 number system, which is actually a weighted number system. That is, the weights are given to specific positions of numbers to determine the value of the exact number. Gray code is a type of binary coded decimal where two successive values differ only by 1 bit. Useful in minimizing errors in rotary encoders and position sensors. It's a self-complementing code or a reflective code. XS3 code. XS3 code is a type of a code which is obtained from BCD by adding 3 to each decimal digit before encoding it to binary. Useful in arithmetic circuits to simplify subtraction. Another type of code is the alphanumeric code, which in many situations digital systems require to handle data that may consist of numerals, letters and special symbols. Therefore, it's necessary to have a binary code for alphabets also. If we use an alphabet binary code, that is, we can represent 2 to the power n elements to this code. We need a minimum of 6 bits, that 2 to the power 6 equal to 64, as we can see in the case of American Standard Code for Information Interchange, that is ASCII code. Next we come to the error detecting and correcting codes. Error detection can be done through parity checks. Parity checks depends upon the number of ones in the numbers. Simplest form of error detection appends an extra beta parity bit to a data string to make a total number of ones, either even or odd, detecting single bit errors. Hamming code is a type of a code that can correct as well as detect both single bit errors. It introduces redundant bits at specific positions of the data, allowing the identification and correction of errors. Cyclic redundancy check, CRC, powerful error detection technique used in digital networks and storage devices. It computes a checksum based on the polynomial division, detecting a wide range of errors. Logic families comes under transistor logic and complementary metal oxide semiconductor characteristics. The first is transistor logic, an older logic family characterized by its bipolar transistor design. TTL uses only transistors, offers high speed but consumes significant power. But as we can see in the case of complementary metal oxide semiconductor, dominant logic family today, known for its low power consumption, high noise immunity, uses both NMOS and PMOS transistors. Key characteristics of both these types is given by power dissipation, switching speed, noise immunity and fan out. Next we come to the basic types of complementary metal oxide semiconductor, how it is designed and the types described in detail. Static CMOS always has a path to either VDD or ground, providing stable and predictable behavior, robust against noise but can be slower than dynamic CMOS. Dynamic CMOS are those type of CMOS which can rely on temporary storage of charge on capacitor. Faster than static CMOS but more susceptible to noise and charge leakage. The design considerations to be kept in mind that the choice between static and dynamic depends on speed and power requirements. Therefore, dynamic CMOS requires careful clocking and charge management too, as we can see from the two diagrams, static and dynamic. Next, we come to the transistor logic family and its types. The standard transistor logic family and Schottky transistor logic family. Standard transistor logic is a type of a TTL that uses two emitter NPN transistors. A standard TTL NAND gate has 4 circuits of 5400 per 740, as we can see from the diagram. Similarly, Schottky transistor logic is a type of a TTL that is used to speed up the operation time of the transistors logic family, and a Schottky TTL circuit provides twice the speed of a high power TTL. Next we come to the last but not the least, the power dissipation in digital circuits. Power dissipation is a critical concern in digital circuit design. It has 3 components: static power, dynamic power and short circuit power. As we can see from the pie chart that the static power, which is given by the Brown combination, is of a medium size, and the most small is the short circuit power. That is, the power dissipation through short circuit is the smallest, and the largest is the power dissipation through dynamic power. Now, what's the three powers actually? Static power is due to leakage current, dynamic power is due to switching transistors, and short circuit is due to both the transistors conducting at the same time for short period during intermediate stages, as we can see from the graph. The transistors operating at different rates and switching at different positions. Also, the lagging occurred at the same time for short period. That's the short circuit power is coming from that. Thank you.